Thanks for joining me today. My name is Rahul. I'm a staff engineer at LinkedIn. And yeah, so this session is about tuning gRPC for high performance. And I'll talk about three things today. So one is deadlines, one is batching, and then KeepAlives. So this session is for you if you have already built gRPC services in production and you want to go beyond the basics that we know. For example, how to tune these settings for production workloads. So gRPC is powerful, but as the system scale in production, then these challenges start to show up. So understanding all these knobs in gRPC like deadlines, batching, and keepalives, it can make a real difference between a system that just works versus a system which can handle, like it can work in cases of low latency, it can achieve high throughput and also stability at scale. Yeah, so gRPC has become the backbone of all the high performance distributed systems. So it gives us a lot of features. For example, it gives us strong typing. We also have protobuf serialization, and we can do efficient binary serialization with protobuf. And it has built-in support for streaming also. So all of these are like very crucial features when you are really trying to move your data across services at scale. But when you start scaling your gRPC services, in production at large scale, then you start seeing all these issues that I mentioned here. So, for example, latency starts to creep up as you make like multiple calls. There are multiple downstream services. So, as the request goes from your upstream to a lot of downstream services, then the latency starts piling up. And also retries. So I'll talk about deadline behavior in the next few slides. So we'll see if we don't coordinate the deadline behavior properly with retries, then we can see a lot of bad behavior in our gRPC services. And also we have connection churn. So by connection churn, I mean connections which are constantly being open and closed. They can cause real issues. So we'll see how can we tune our keep alive settings if we want to get rid of that. And also we have a lot of, for example, we have load balancers, we have Envoy proxies. So like getting our gRPC request across all these services will like further worsens all these three challenges. So like in this talk, I'll focus on these three tuning levers that can really move the needle in production: the deadlines, batching, and keep alive. And we'll see how we can properly configure our retry behavior using deadlines. We'll see why batching is like very much needed for especially for CPU workloads, and also how we can use keep alive pings for like real world load balancer setups. So let's first look at deadlines. So deadlines, they are the one of the most important knobs of gRPC. So they specify how long basically client has to wait for the request before actually giving up. So we can think of it as a request budget. So when you start a request from a client, you take some budget, for example 10 second, that's a lot, or 20 second, and then once that runs out across the whole stack of services, then your call gets cancelled, then you start seeing context deadline errors. So what's tricky in that is that deadlines actually travel downstream also. So in this example, you can see we have two downstream services. So in this case, let's say you're calling service A and then that calls service B. So each hop in this case will see a shorter remaining time. So let's say if you start with a budget of anything, then it gets consumed at every service layer, and then as you move ahead, it will further you will the last service will like remain with a very less budget. So in this case, if you have like a deep stack of services, then the services which is at the last downstream, it won't have any meaningful time to do its actual work. So this is a simple example of configuring deadlines. So on the client side, we can see that it sets a deadline of 1.5 seconds. Now, if the server doesn't respond in time, then it will throw this deadline exceeded error. So on the server side, we have a simple check. Using that check, we just see that what's the remaining time left in this case. In this code example, we are checking that if it's less than 50 millisecond, then it's better to fail fast rather than actually starting work. Because for this example, I've assumed that in 50 millisecond, there won't be any meaningful work that the server will able to do. So in this case, it's better to just fail fast here, not even try to start the work, and then just throw the deadline exceeded error. So this will prevent at least resources not from getting wasted. It will keep the system stable. So deadline in this case, it also enforces predictability. So it gives us a consistent way to just budget our whole time that we have across the services. It also has impact on retries, which we'll see next. So in this case, let's see how deadlines work with retries. So when a deadline expires, then in this case, gRPC won't even retry this call. And that makes sense because if the client already has given up in this case, then there is no point in retrying this call. So, but there are a few things, a few ways in which we can configure the deadline with retries. For example, let's say if a client sets a very short deadline, but it allows multiple retries, then we know that all of these retries are eventually going to fail. We have a very short deadline. So in this case, there's no point of retrying the request. On the other side, let's say if we set a very long deadline, then in this case, the retries will just start keep piling up. It will just add unnecessary load on your service. Another case here is mismatched deadlines. So a common issue is that when your upstream service that is setting a longer deadlines than the downstream ones. So for example, imagine your client sets a deadline of 10 seconds, but your downstream service it only enforces a 2-second deadline. So in this case, if there are many upstream clients in this case, so all of them will just retry because they have a longer deadline of 10 seconds. They will keep retrying. So in this case, the downstream service will just it will keep getting hammered with a lot of calls from upstream, and it won't be able to satisfy any of those requests or some of the requests because it has a deadline of only 2 seconds. So that will just burn the CPU, it will burn the memory, and like here we are not doing any like productive work, just wasting CPU and memory. So another thing is the precision loss that we can see in case of this timeout header. So gRPC, it doesn't actually sets the timeline as absolute timestamps. So there's a gRPC timeout header which you can see. So it just tells us how much time that we have left like from that point of time. So for example, if this header has a value of 251 milliseconds, let's say, then from that point of time to all the like services which are there downstream, they've only got a total of 250 milliseconds to do all of their work. So now in this case, let's say we have a lot of proxies in the middle, we have a lot of sidecars. So all of them will first try to look at that header, and they might try to do some calculations. For example, 251 millisecond. Let's say if they try to read that value and do some of their own calculations, they might try to round off this value to by half a second or 1 millisecond or so. Sorry, not half a second, just half millisecond or so. So let's say if one service rounds down it to from 251 millisecond to 250 millisecond. So on one service it looks harmless, but let's say you have got multiple hops, and let's say you have got an API gateway, there's a service mesh, a load balancer. So if each one is taking this half millisecond or 1 millisecond, then it will, in the end, you will see there is not much time left to do any work. And then we have queuing delays also in between all these calls. So queuing delays will further like worsen this, and then it will reduce the timeout to a very small value. So in this case, the backend will see there is no time left. It will again cancel the call. The client will again see this deadline exceeded error. The way to prevent this is simple. So instead of just relying on this relative value that is carried in this timeout header, we can just carry an absolute deadline inside your context. So at each hop in the service, we can just compute this relative value again, for example, this gRPC timeout header, and then we can set it from the absolute deadline that we have remaining. Clamping also we can make sure that we just clamp it to a safe minimum, so that small rounding errors that we are seeing, it just doesn't make this value to complete zero. Another thing is, another issue is retry and hedge amplification in case of gRPC services. So let's say if you set a long end-to-end deadline, but let's say each attempt that the service is getting, it's very small, then in this case, the client is just going to do a lot of retries. So now, since each request has got a very small timeout, so each one will just fail instantly. In this case, again, we are just burning CPU and network resources. We are just retrying a lot of time, but the service is not doing any actual work here. And again, in case of hedging, by hedging I mean that let's say you have to send multiple copies of the same request parallelly. So and hedging is like mostly it's done with some time of like a small amount of hedging delay. For example, if you send one request to a service, you want to wait for a few milliseconds, let's say a few seconds, before you send the same copy of the request to another service. And this we do because we don't like rely on one service returning the correct result to us in time. So we want to make sure that okay, we are sending multiple copies. So in this case, if there is, let's say if there is not much left time left in the overall budget, in the overall deadline, then hedging is just going to again like flood your downstream service, and again the downstream service won't have the time left to do any work. So the way to fix this is to like first we have to set meaningful per attempt budgets. So we have to make sure that we are giving each request like ample amount of time to succeed, otherwise it will just fail. And also we can cap on the maximum number of attempts that the service is making, so that your system doesn't just keep on retrying infinitely. And finally, one other thing is that we can also check, like let's say if we are trying to enable hedging, we can also see that the remaining time, whatever we have left, is less than the round trip latency. For example, in this case, we are checking the median latency that each round trip time takes, and then we can see if we don't have enough time left, even for a median request to come back, then we don't have to just do hedging at all. Then we know that we are just going to simply waste resources. So okay, now let's see what batching means in case of gRPC services. So as the name suggests, I think it's conceptually simple. So instead of firing just one RPC request every item, we just let a tiny queue, like we just create a tiny queue on the client side, and we just bundle all these requests together. So instead of sending one request like for every item, we just will batch them. We'll send them at once, and we'll also in this case we'll just get one response, which will have all the results like for all the RPC request. And that like pays off in both these cases. So first on the CPU path, so we spend like time to do protobuf encode decode. We do object allocation, header passing. So all of these I think take some amount of time. So if you are doing batching of the request, then you are paying the price just once instead of paying this price every time for every request. So in this case, we just let the CPU do more work. We stop suffocating the CPU in doing all this encoding, decoding, passing of headers. Second, on the wire also, if you have fewer round trips, fewer calls, sorry, it will mean fewer round trips for the request. It will also mean you will have few response and request headers. You will have few control flow events. So now we also have proxies and servers like in between. It will, in this case, if you are batching the request, it will just see less amount of chatter. The congestion that it sees in case if you're firing a lot of RPC requests, that will also go down. Your tail latencies also, everything will calm down. So in this case, you saw that we, I think, paid a small price on the client side in terms of timing, because we want to wait for all the RPC requests to first batch, and then like we want to solve a bunch of issues just by paying a small time price in this case with queuing. So batching, it matters like a lot when your workload is mostly CPU bound. So ML inference is one example. Mostly now we also do ML inference in case of GPUs. But let's say if we want to run inference on CPU, so instead of just pushing one item through the model, yeah, sorry, 5 minutes, okay. We just let a tiny queue, like create a tiny queue on the client side, and we want to batch them in terms of, let's say, 16 or 64 items. So in this case, now your kernel will run the vectorized operation. In this case, you will also be able to fully utilize your GPU, because GPU has a lot of cores. So you will achieve high throughput, and you will stop paying the fixed cost over and over. So in case of streaming also, like in case of streaming traffic, it mostly doesn't arrive evenly. You will get traffic in sometimes in bursts also. So if we send every message again as its own RPC, your system is going to get overwhelmed with a lot of timing calls. So with micro batches, we can create a small window. So you can do this either, let's say you want to flush every, let's say, group of items. For example, you want to wait for 16 or 64 items to arrive, then you want to flush it. Or you can also do it like based on a time window. For example, you want to wait for 10 milliseconds and then you just want to flush the request, like batch the request and then send it. Yeah, so I have a few minutes left, so I'll try to cover the remaining slides. Yeah, so a simple example in Go that takes the incoming jobs and it tries to batch them together. So in this case, we keep a memory like buffer of all the jobs. So each job has a request payload and a callback also for returning the result. So I mentioned the two strategies that we can use for creating the buffer, for flushing the buffer, sorry, that we can use. So one is the size based that we have, that we want to hit the maximum size and then we want to create the batch and then send it. And then other can be time based, that we just want to wait till our timer expires. So we can wait for a few milliseconds, a few hundred milliseconds, and then just whatever request is available at that point, we can just batch and send it. So when we flush it, we build a single batch RPC with all the requests. We then send it to the our inference service or the server. So in this case, if let's say if the RPC fails, we can fail all the jobs in the batch. And if let's say it succeeds, then we'll send the using the callback response to each of the individual callers. So on the bottom, we just have a simple loop, the event loop that runs continuously. It just, if the new batches, if the new job arrives, it's adding it to the queue. And if the buffer fails or the timer is firing, then we just flush the request. Okay. So the last thing that I want to talk is KeepAlives. So KeepAlives are early warning systems for us. So they can help us detect a lot of things. For example, Wi-Fi flips, if there's an idle, let's say, connection drop, or if there's a mobile sleep. They also help to keep the NAT and load balancer mappings warm, so that your link is doesn't expiring quietly. The link that the load balancer maintains, it doesn't expire quietly. In this example, a network translation device, so or let's say load balancer, it just keeps a mapping or a connection table between the client and the server that it wants to send the request to. So each of these entries has a timeout. So let's say if there is no packet flow for about 60 seconds or so, it will assume that this connection is dead and it will try to just delete this from its table. So in case of KeepAlive, the client will just send small HTTP2 ping and it will expect an ACK in response of that. Let's say it can send it every 45 seconds or so. So in this case, the load balancer or the NAT service, it is treating this as the real traffic, and the timer that was getting expired, that won't happen now, because it knows that, okay, it has to keep this connection warm. Okay, so let me cover the remaining slides quickly. So when we set KeepAlives, when we tune these settings in gRPC, so the first habit is to always align them with the actual network path. So every NAT service or a load balancer or proxy, it usually has its own timeout. So let's say if they are configured to drop the connections every 60 seconds or so, then we don't want to send these pings after those 60 seconds, like every 2 minutes. So we want that because if we send it after 2 minutes, we know that the load balancer is going to expire the connection, reap the connection. So we can set our KeepAlive timeout to about 70 to 80% of the shortest idle timeout that we know. In this case, we can set it to about 45 or 50 seconds. And accordingly, we can set a small timeout window also. So in this case, again, now let's say 1,000 of clients, they will try to fire a ping exactly at 45 seconds. That will again create the phenomenon like called as thundering herd, when your downstream service is getting hammered from a lot of calls. So to avoid that, again, we can add some small jitter between the clients also, let's say plus or minus 15-20%. So the pings are like more spread out over time. And finally, so in gRPC, so we should prefer using the built-in HTTP2 ping that we have for KeepAlives. So there's a OS level TCP KeepAlive also, but the gRPC one is more lighter weight, more precise. So if we want to use them both, we should just try to not set them at the same cadence, because then they will just interfere with each other. Your downstream service is going to just see double the noise. Yeah, and again, some more guardrails about keepalives. So on the server side, we should just not accept any keepalive behavior. We should enforce guardrails. So the first one is the minimum ping interval. So if a client tries to, let's say, ping too frequently, then that is considered either a misconfiguration or abuse. So that we should not allow. And also there is the permit without stream setting that we should keep off by default. So it means the clients they should not send keepalives on just completely idle connection. So there are special like exceptions in this case where they can do it. For example, control planes or long-lived subscribers, mobile networks. Usually they want to keep the connection open for a long time, even though they are idle. So apart from those cases, we should just turn this off by default. And if a client violates any of these policies, we can send the go away signal. So that's the HTTP2 way of saying that this correction is now out of policy. So you should just reconnect with the right settings again. And the last point is, yeah, we can even auto tune the guardrails also that we have set. So for example, imagine a case where a phone that's switching from one network to another. In this case, the load balancer mapping that is there, that will go off, that will expire. So if we wait for this like pre-configured time, let's say 45 or 50 seconds to ping the next alive, then the client won't notice that the path is broken. Your RPC will fail in this case. So in this case, we should just tune it accordingly. In this case, we should shorten the interval to make this keep alive pings. So that will just try to revalidate the connection. Yeah, I think, yeah, that's all I had. Yeah. Thanks for attending.